Imagine stepping back in time, 2 billion years into Earth's past. This era teems with life, yet it also witnesses widespread devastation. An unseen force emerges, poised to reshape the planet's destiny. The events unfolding here profoundly influence the world as it exists now, the creatures that roam it, the sustenance we derive, the very air that sustains us. Journey with me to this ancient Earth, roughly midway through its lifespan so far. As you approach, vast expanses of ocean separate scattered landforms and occasional icy patches. These terrains bear no resemblance to modern continents, though transformations loom on the horizon. Upon arrival, the vista unfolds as a stark, rugged expanse, devoid of flora, absent of foliage or any verdant cover. No creatures stir. This precedes the dawn of intricate multicellular forms. Life manifests solely as minuscule entities, perhaps unexciting, yet reassuringly free of threats. Before venturing forth, equip yourself with a breathing apparatus, for while oxygen lingers in the atmosphere, its concentration falls far short of what's needed for ease. It amounts to less than 1/10 of contemporary levels. In Earth's infancy, the air held only carbon dioxide, methane, and water vapor. More on that shortly. Gazing into the surrounding waters, they appear tranquil, empty of aquatic life, yet they brim with verdant, viscous masses. These are cyanobacteria, among the most pivotal organisms to grace the planet. They forge the breathable air we know, but they also trigger the greatest die-off ever recorded. To unravel this cataclysm, we must delve deeper into the past, another 500 million years. Here, oxygen is utterly absent from the air. The planet differs markedly from familiarity, yet foundational elements persist. Elements like uranium, born in the universe's nascent throes, have embedded themselves in Earth since its formation. Such substances hold enduring significance in the planet's saga. Returning to the microbial realm, bacteria dominate, much as they do in later epochs, often stirring profound shifts. Let's revisit Earth around 2.5 billion years ago. On the cusp of calamity, serenity prevails. The youthful sun shines fainter and cooler. Surface temperatures hover warmly, fostering abundant liquid water without polar caps. The atmosphere's carbon dioxide and methane fuel a potent warming effect. Life thrives exclusively in aquatic realms, single-celled beings, unassuming yet transformative. Amid them, cyanobacteria emerge, endowed with a remarkable capability harnessing water for photosynthesis, yielding oxygen as a byproduct. As these cyanobacteria proliferate into vast communities, oxygen production escalates. Initially, much of it binds with minerals, vanishing from circulation, but over ensuing hundreds of millions of years, accumulation overwhelms absorption. Waters saturate with oxygen, which then permeates the air, reacting with and displacing methane. The atmosphere evolves, becoming increasingly hospitable. Yet oxygen remains modest, perhaps 1/10 to 2/5 of present amounts, or even less. For anaerobic bacteria, this surge proves lethal, a toxin eradicating vast populations. This marks the Great Oxidation Event, history's most colossal extinction, claiming 99% of earthly life. Beyond the microbial toll, atmospheric upheaval extends further. Cyanobacteria not only generate oxygen, but deplete key greenhouse agents, carbon dioxide and methane, that once insulated the planet against chill. With their diminution, cooling intensifies dramatically. Across hundreds of millions of years, the landscape morphs profoundly. Oceans solidify into ice, blanketing the globe in frozen veils. Barren terrains turn pristine white under snow. Thus commences one of the planet's initial ice ages, the Huronian glaciation, enduring roughly 200 million years. It encompasses 3 glacial phases, sparing no region from equatorial seas to continental interiors. Life, already ravaged, faces further peril from oxygen's poison and unrelenting frost. Yet a resilient fraction, scarcely 1%, endures in isolated refuges, biding time until thaw. As epochs advance, renewal stirs. The sun grows subtly brighter, its radiance amplifying by about 1 degree Celsius every 100 million years, now 5 degrees warmer than before. This alone insufficient for melt. Another force intervenes: volcanic fury. Beneath the icy veneer, Earth's core simmers. Tectonic forces unleash a torrent of eruptions, persisting for 300 million years. Dispersed landmasses converge, forging the inaugural supercontinent, Nuna. These volcanoes reshape the air, expelling water vapor and carbon dioxide unchecked by microbes. Accumulation ensues, trapping heat and escalating warmth. Ice recedes, unveiling a revitalized world. The eruption's legacy lingers. Lava facilitates carbon's metamorphosis into diamonds, many traceable to this period. Concurrently, in Africa's depths, an extraordinary phenomenon unfolds: nature's inaugural nuclear reactor. Earth's formation accrued uranium from cosmic debris, forged in stellar explosions. Microbial and tectonic actions concentrated, igniting fission. Atoms split, neutrons cascade, sustaining a chain reaction, a natural marvel. Collectively, the intensifying sun, volcanic emissions, and localized nuclear heat propel warming. Waters prevail over ice. Nuna's expanse contracts. Surviving microbes flourish anew. In oxygen-enriched environs, novel forms arise: organisms that inhale oxygen, metabolize sustenance, and exhale carbon dioxide. This reciprocates with cyanobacteria, fueling further oxygen via photosynthesis, a cycle mirroring today's interplay between respiring beings and photosynthesizers. Oxygen's ascent crafts a shielding stratum aloft the ozone layer, deflecting harmful ultraviolet rays. This safeguards emerging life, enabling habitation in shallow waters. Harnessing solar energy safely. Cellular complexity advances. Nuclei delineate, birthing eukaryotic cells. These pave the way for flora, inheriting photosynthetic prowess from cyanobacteria. Diverse entities materialize: multicellular fossils reveal soft-bodied marine dwellers, varying in scale, some spanning 17 centimeters. They burrow in sediments, thriving amid elevated oxygen, though eventual vanishing leaves no lineage. Their multicellular framework underpins all subsequent complex life: flora, fauna, fungi, and more. Ancient algae endure in stromatolites, fossilized formations enduring to this day. These primordial upheavals, geological and biological, underpin contemporary existence: the oxygen we inhale, chlorophyll sustaining vegetation, our multicellular essence, and the ozone's vigil. The ancient tapestry weaves the fabric of life as we know it.